After doing the case one, let's focus on the case two. Case one, crossing the river, the swimmer or the boat just starts entering the river at once, right? And then at the end of the day, because of the velocity of the river, the body is pushed um, farther away from the intended location or intended destination at the other bank. We look at that and solve two examples in the previous sessions. Now, in this case, too, what we actually want to do is that we don't want to we want to exactly arrive at a particular destination on the other bank. Okay, we want to cross the river and arrive exactly at the point opposite us. That's where we want to be. We don't want the river to push us away from where we want to reach when we are crossing the river and reaching the other bank, right? Now we need to actually now look at how we can position ourselves, or how we need to jump, in which direction we need to jump, or we need to start the journey at the starting bank in order to arrive at the intended location at the other bank, right? That's what we are going to. That's the case two about. Case two is one. We saw that we start the boat exactly facing the front in order to reach there. At the end of the day, because the river is having a velocity, it pushes us on the side. But because but in this case, we want to actually arrive there, and we want to keep in mind the velocity of the river, that the river will be pushing us. So we need to account for that and turn in a particular direction, so that when we are just crossing, at the end of the day, we reach exactly where we want to reach. Just like the picture over here, people like this that are swimming, right? They are applying this all the time. They are applying this all the time because they are in a race, and then they need to arrive at a particular position. So they consider how they can turn, how the river is moving, all that in mind. We are going to do simple cases. Of course, we are going to start with solving question. This question we have solved it already, but it was in the format of the case one. But in this case, look at what the question is saying. A boat crosses 5 kilometers wide in 30 minutes in still water. The river flows at 4 kilometers per hour. In what direction should the boat be set to arrive exactly at the opposite side of the bank? So we have such an example. So we are here. This is Bank A, and then this is Bank B. And we are somewhere here. And we want to reach here. Let me call this one small b, and this is small a, right? We want to move from here and reach here. Exactly. This is where we want to reach. This is where we want to reach. We want to move from here to here. But the river is also flowing at a particular velocity. From case one, we saw that if we jump into the river from here, directly facing here, at the end of the day, the river will be pushing us, and then we will reach here at the end of the day because of the velocity of the river, right? But then what can we do? Since the river is flowing in this direction, and we know that at the end of the day it will push us, why don't we turn this way? Why don't we turn this way? When we turn this way, then the river will be, when we are crossing, by the time we reach here, the river will be pushing us, and then we'll actually arrive here, right? We don't jump in directly, but we jump in a particular direction in such a way, and we swim in that direction, such a way that at the end of the day, we are able to reach exactly here when the river is able to push us. Okay. So we are not just going to jump into it directly, but we are going to turn in a direction like this. And because the river is flowing like this, and we know it will push us. So when it's pushing us, it will push us. At the end of the day, we'll reach exactly here. So that's why we need to. If the river were flowing here like this, if the river was flowing like this, then we need to jump inside like this, so that by the time it's pushing us, it will make us arrive at the exact location. That's what the case two is all about, right? You jump into the river in a particular direction such that at the end of the day, the effect of the river will make you arrive exactly at point B. So let's solve this question. So we solved this similar question with the same data before. So 5 kilometers in 30 minutes, right? We said so the displacement is 5 kilometers. That's still water thing. And then 30 minutes. 30 minutes, that's 60 over 30. That's half an hour, right? Yes, that's half an hour. 30 minutes, that's half an hour. That's 0.5 hour. So when you do this, the velocity of the man is actually 10 kilometers per hour. We've solved this in the previous session. Okay. Now we are not jumping directly, as you said. We are now going to turn in a particular direction. So the river is flowing in this way. So we need to jump in here in this direction, right? We are going to jump in somewhere in this direction, but we need to actually find that particular direction. At the end of the day, how would this thing look like? So we'll turn like this. We'll we'll take this direction, right? And we know the river is flowing this way. So the river is like this. What happens? Then if you take that thing out, you actually have your resultant velocity here, and then your this is the velocity of the river, small r, and this is the velocity of the boat, right? This is you, and this is the resultant velocity now. Okay, so we have right angle triangle now. This is as our velocity is now the hypotenuse, and then um the VR is now the velocity of the river. But in what direction should we turn? We are looking for this theta, right? If you look for this theta, remember it's just this theta between this and that. But we are looking for the direction related to the bank. Let's call it alpha. Alpha. So how do we get that theta? Right? We know the hypotenuse and we know the velocity of the river. So we know that for the angle, um, opposite, this is the opposite side, and this is the hypotenuse now. The hypotenuse is this side, and then this is the opposite side to this angle. So SOHCAHTOA, opposite over adjacent. Opposite over adjacent. No, opposite over hypotenuse. So is sine is equal to opposite over hypotenuse, right? So we know the opposite. So sine theta will be equal to the opposite side. The opposite side is the velocity of the river over the hypotenuse. The hypotenuse in this case now is our own velocity of the boat. So we need to find theta. Theta is equal to sine inverse of VR over VB. VR is 4 kilometers per hour and this is 10 kilometers per hour. So if you do that, you are going to have 0.4. If that's the case, then let me quickly get that into the calculator. Where are you? Where are you? Yeah. Sine inverse of 0.4, 23.578. I got 23. So sine inverse of whatever we have, right? I didn't write this thing well. Let me write it well for you. Or let me even go to a new page. So we are doing theta is equal to sine inverse of 4 over 10, which is 0.4. Then I said I got 23.5782. 5782 degrees. Remember what we got, this angle theta is this theta, but the bank of the river is like this. We are looking at the direction that it makes with the bank. In which direction should we jump relative to the bank? Relative to the bank. This is the bank, this side is the bank, right? So we got theta, but we should be able to find alpha from here. Theta plus alpha is always 90 degrees. So theta plus alpha is 90 degrees, right? And we know theta, so we are looking for alpha. Alpha is the velocity, is the direction related to the bank. 90 minus 23.5782. Then I got 90 minus, so the answer will be, sorry, the final answer will be 90 minus the previous answer, 66.42. So 66.42 degrees. So yeah, this is the direction we need to jump into the river relative to the bank, right? So relative to the bank of the river, we need to move, like jump into the river or start the boat in this particular direction. That's 66.42 degrees exactly. So by the end, by the time that we will cross the river, right, we will be able to arrive here exactly. exactly as we said. So from here, you can they ask you to find the resultant velocity in an order. The resultant velocity is equal to the square of the hypotenuse and then all that, right? We consider the right angle triangle like we said. So it's going to be VR is going to be equal to square root of the hypotenuse squared, that's the VB squared, minus V of the river squared. That's how you find the magnitude of the resultant velocity. But yeah, we are more concerned about the direction that we actually take in this case. Yeah.